we're going to talk about some applications of the equipartition theorem. The first one is the specific heat of a monatomic ideal gas. So in the case of this monatomic ideal gas, there is only one contribution to the energy, total energy of the gas, that is the kinetic energy of the translational motion of the molecules. So let's note that we have only kinetic energy contribution, and that comes from the translational motion of the center of mass. So due to translational motion of molecules. And that means we're going to have for x, y, and z directions, if this is in a three-dimensional container, then we have 1 over 2m px squared, x component, 1 over 2m py squared, plus 1 over 2m pz squared. So this is basically what I called epsilon I in the derivation of the equipartition theorem, that consists of an epsilon x, epsilon y, and epsilon z. And epsilon x, y, and z, they only have a quadratic term in momentum. So therefore, using the equipartition theorem, the mean energy for each of these components will be equal to 1 over 2 thermal energy, kT. So for epsilon x, epsilon y, and epsilon z. Therefore, we find that the mean energy per molecule will be equal to 3 over 2 kT. So this is mean energy per molecule. Now, if you have a total of capital N molecules, then for capital N molecules, we can write the total mean energy. This is going to be capital N times the mean energy per molecule, epsilon bar. So this will be equal to 3 over 2 nkt. And for 1 mole, we have the number of molecules is equal to Avogadro's number, 6.02 10 to 23 molecules. Then we have for the mean energy 3 over 2 Avogadro's number, kT. But since universal gas constant R is equal to Avogadro's number times Boltzmann constant K, we can write the total mean energy as 3 over 2 RT for 1 mole. So this is the mean energy per mole, 3 over 2 RT. So if you want to know what is the molar specific heat, then we can calculate the molar specific heat at constant volume, so that we have only thermal interaction, no work done on the system. So this is going to guarantee that we have work done is 0 thermal interaction. And in that case, CV, and remember that we use the lowercase letter c for specific heat, CV, molar specific heat, heat capacity per mole, is the derivative of the mean energy with respect to temperature evaluated at constant volume. So this will be equal to 3 over 2 R. So we find that the molar specific heat of a monatomic ideal gas is equal to 3 over 2 R at constant volume. So this is the first application we will talk about. So just to summarize, in the case of a monatomic ideal gas, we have the only contribution to the energy coming from translations of the center of mass, and that is giving us a kinetic energy contribution 1 over 2m px squared plus py squared plus pz squared. So if you remember, epsilon I was what I called the term in the energy that depends on momentum only, and that is basically epsilon x plus epsilon y plus epsilon z for the total energy of one molecule. So according to equipartition theorem, the mean values should be 1 over 2 kT per degree of freedom. That has a quadratic contribution to energy. So 3 over 2 kT is the mean energy per molecule. For capital N molecules, 3 over 2 capital N kT. For 1 mole, 3 over 2 RT, and the molar specific heat at constant volume, so that we have only thermal interaction, will give us 3 over 2 R for the case of a monatomic ideal gas.